Muito bom dia a cada um dos que aqui está hoje conosco, na comemoração dos 30 anos do CBQF, em mais um seminário. No fim deste seminário serão colocadas ao nosso orador principal as questões que nos queiram ir colocando no Q&A, no vosso sistema. Por isso, apelamos à participação de todos. Sem mais delongas, passo a palavra à sua professora Manuela Pintado, diretora do CBQF.
Bom dia a todos, é com muito gosto que estou aqui hoje a celebrar mais um momento dos 30 anos. Os 30 anos do CBQF celebram-se ao longo do ano, iniciamos a 24 de novembro e estarão representados em várias iniciativas até final de outubro. E, portanto, é com muito gosto que hoje abrimos mais uma iniciativa e que eu gostaria aqui de reconhecer também a alegria que tenho de poder cruzar a nossa iniciativa de celebração dos 30 anos com a oportunidade das jornadas de biotecnologia organizadas pelos nossos estudantes e que me deixa muito feliz, e a todo o CBQF, por conseguirmos cruzar aqui esta oportunidade única de cruzar o conhecimento da ciência com o interesse dos nossos alunos e, portanto, agradeço uma vez mais essa oportunidade e também agradeço muito, e agora vou mudar para inglês para que o professor Saeid me consiga perceber, dizer só umas breves palavras. So just to turn to in English, Professor Saeid Sanei, just to inform you and to communicate you that we are celebrating throughout the year, since November until October, we are celebrating the 30 years of CBQF with different workshops, initiatives. So I'm really pleased to receive you and welcome you to our celebration moment, and thank you for this. I know you are a busy researcher and professor, so we want to thank you so much for being today with us, and leave just a moment to Pedro Rodrigues to present you in detail, and I wish you that you can receive you another moment face to face to join with us with your science. Thank you so much.
Pedro, tens que ligar o microfone.
I'm sorry, I was muted. Thank you, everyone. Thank you, Manuela, for your nice words. Welcome, everyone, and thanks for your presence here. Today, we are once again celebrating the anniversary of 30 years of CBQF, and we count on the presence of a very special guest that must honor us with his presence. I'm talking about the prestigious Professor Saeid Sanei, with a long track record and experience in signal processing area and artificial intelligence applied to healthcare. Professor Saeid, I must say it, is one of the most well-known references in this field in worldwide. For me, it's really an honor to have him with us today. Let me tell you a little secret. The book EEG Signal Processing publishes, hope I'm not wrong, in 2007. I have him on my vitrine. Still need a sign from Professor Saeid. And one day we will be face to face for sure. He will bring me the honor to sign it. Marked me strongly and greatly influenced my taste in this research area. I take this opportunity to thank Professor for having edited together with Professor Chamber this magnificent book. Let's move on. Today, Professor Saeid is going to talk about digital health through signal processing and artificial intelligence. And right now, I will address some words to Professor Saeid. Thank you once again very much for your presence and for accepting our invitation. I have been consulting your vast...
Unmute myself, okay. Well, thank you very much indeed, first, Pedro. I think it was too much for me. I'm really honored to be with you here, and I hope it's going to last forever, so we can continue this. But don't make me believe that I'm somebody. I'm not anybody. So please don't go that far, okay? Okay, thank you. So let me share the screen with you, and then just give you some ideas of what's happening around the world on these topics. And hopefully we can start chatting together and discover more about it. Okay, so let me see whether I can share the screen now. Yes. Okay.
I just remember you that you have about 14 minutes, more or less, to perform your presentation. Yeah, and after it, I will open the debate to the auditorium. Okay.
Okay. Okay. Can you please let me know if you see my screen now?
Yeah, that's okay.
Blue one. Okay.
Perfect.
Yeah.
Thank you.
Okay. Thank you very much, everybody. It's again really pleasure to be with you. And I'm really glad that I'm with you on this celebrated event and celebrated time that you have in Porto on CBQF 30th anniversary. First of all, I have to talk about why I decided to choose digital health. Well, I'm actually a visiting academic in digital health in Imperial College, London, but there is really no idea of what is happening. But when you Google digital health, you see a lot of keywords. It can refer to data collection. It can refer to processing and transmission of the data. It can refer to making sense of the data, which is important nowadays. And then some applications like mobile health and health information technology and wearable devices and body sensor networking, which is of particular interest to me. Then there are similar items like telehealth and telemedicine and such like, and personal medicine. And of course, at the end, it reaches to AI for automatic decision making. Now, if I go back, let me see whether I can remove these things from the screen. Okay, now I borrowed a couple of slides from different people that I met them in the previous conference that I organized myself. One of them was Sir David John Espenholter from Cambridge, that you might have seen him in news or in actually in many events and media and all these things. So he's a very famous person. I'm just trying, sorry, to minimize this. Okay, that should be fine now. Okay, so the first thing that came to my mind when I wanted to prepare my talk today was talking about uncertainty and something which at the beginning of the day and at the end of the day is going to scratch different people's minds. So why uncertainty is important? And I looked at the work of John Espenholter, that all his life was working on this uncertainty. So what he mentioned in his talk was that there is no aim at increasing trust, basically, just because there is uncertainty, but we should trust, we should demonstrate somehow what we call it as trustworthiness. So we have to believe in this uncertainty. So if we label a data, we should believe that there is uncertainty in that. If we observe data, we have to look into this one. And we have to believe, again, that data and information should be first accessible, then intelligible, and then usable, and then accessible. And if you really have all these things, then you should be able to have a good measure of so-called uncertainty in the data. So there are always this misunderstanding between uncertainty and causality, actually, that we have, and we use them. So of course, the idea is to believe in uncertainty, and then the other belief is really to find a link, so to work on all these things, to find some causality relation and try to expose or try to use even this uncertainty. So I come back to this one, of course, later. And then I came back to the work of Hermann Ney. Some of you may know that perhaps about 30, 40 years ago, about maybe 36, 37 years ago, he actually established the first text-to-speech for different languages in Germany. And I can mention that he really had huge contribution into AI system, particularly for audio and video, but unbelievably by use of Bayes decision theory, which is originated in signal processing. So he actually used somehow this uncertainty in order to actually make this decision theory, and from there go to this learning. Now, if you really want to see what is the real capability of AI, you have to look at this way. If you just turn back around yourself and give yourself about 5 seconds to look at what is going on around the room that you're sitting, and then come back and then you think about what you saw, you may have some idea of very, very what you call it, superficial or very brief type of idea, that what different things, what different items you could see around your own room. And now if you do another time, obviously you will pay attention to more information and more detail. However, you now can see the visualization of you and visualization of a computer vision system. So a computer vision system can just go back, take a shot of the image of the scene, whatever is in the room, and then based on what you asked or what you already taught to the machine, can decide what objects are in the room or what objects are of interest. So basically, the only thing you need to do is just to teach the machine what to do and what to see. Although this may take time, but later when you leave that machine to operate, it doesn't need more than few, maybe microseconds to tell you exactly what are around you. So that is really the difference between what a human can have, or has impression around from around himself, or a machine. Now, if we go back to model-driven systems in AI, you normally need to put a lot of effort, or human effort, on telling the machine that what you really to look for, what objects you need to look for in the scene, what the object should look like, and all these things, and then try to work with a lot of maybe geometrical invariant system or scaling invariant system, and all teach this to the machine in order to decide, for example, what is the object of interest. For example, in this hand, where is that particular carpal bone in the hand? So you can imagine that even after all these things, you either have a lot of answers, which means it is going to increase your false positives, or you are going to have some errors. Now you can go to some data-driven techniques, and in data-driven techniques, you can actually let the system to learn rather than you tell the system to decide what to do. So basically, the system can go through more data and can observe more data rather than just looking at the back of the scene of your room. So it can go out and look at different types of scenes around the world, and then finally come back and say, okay, well, now we have a lot of things, and we can, based on what you, for example, decide, I can see whether in your room you have, for example, a telephone at some corner or not. So these data-driven methods that now they are becoming very popular by means of deep neural networks can tell you in a better way that where that carpal bone is. And not only that, they can tell you also that with what level of confidence or what level of certainty they picked up that carpal bone. So you can see these two shots of two different systems, because obviously in the first one you could have more clear image, so the confidence level was higher, and the next one is with more blurry image and the confidence level is lower. Now, if we come back to the link between signal processing and machine learning, you can see that signal processing originates from mathematical foundations. And you can think of some methods like, for example, Fourier transform, that manage finally to summarize or abstract a sine wave which goes from -infinity to infinity into one sample only. And that sample reflects a certain frequency. You can imagine that how a technique or a novel algorithm in signal processing can really change the world. So you can see from that simple technique. Now, there are other methods, of course, which have been developed gradually and still is being developed, like linear algebra, other data transform, and also looking at the distribution, how you can estimate the distribution from long or short data and such like. Now, when we come to machine learning and information theoretic, what we expect is that there are some still barriers, like we need, if we are going to analyze our system, we have to have linear assumption about the system, or Gaussianity assumption, or stationarity assumption. So the objective of machine learning have been somehow gradually to remove this barrier and make sure that the system can easily deal with any type of data. Of course, the same happened in the area of machine learning and neural networks, because that was the time that machine learning started creating so-called generative models. And generative models are basically those models that they can sit and they can look at the environment and then produce something of interest and something which or not interest. So data, as the more data became available, obviously, and the more data analysis became popular and the power of the system increased, you can imagine that the power of machine learning actually increased. A new algorithm came with more complexity and more refinement, actually. Now, there are many methods that can signal processing and machine learning can meet. Nowadays, you might have heard of graphical model and kernel methods, data-driven adaptive system on models, pattern recognition and classification, distributed Bayesian subspace, manifold subspace, or manifold and sparsity aware learning. So how to, basically, this means how to best use the diversity in the data. So you do not need necessarily, like a deep neural network, to look at only the time pattern of the data or the image pattern of the data. There are some underlying factors that can be exposed by the basically power of signal processing in order to make life easier. Now, you have multi-set data analysis, multimodal data fusion, particularly when you are dealing with different types of measurements, perceptual signal processing in audio, image, and cognitive information processing, and multi-channel, of course, adaptive systems, which are highly used in control. Now, when we go back to the president, the ex-president of IEEE, that actually is a purely signal processing man, then he says, well, we can actually use signal processing to apply to data to generate science, because signal processing can reveal the underlying properties of the data. Of course, he exaggerates a little bit, and I tell you why he exaggerates. And now when you come to AI or machine learning, then what you believe is that you have the data, and at the end of that, you have recognition and decision. And then, of course, if you want to link these two together, you expect that your signal processing should generate a model for you and do all these adaptive learning system stuff, formulation and everything, in order to make that to make your AI or machine learning tool able to recognize the or to decide or to recognize the data. However, I really cannot say that both of them are very correct, because when you look at the new deep learning methods, you will see that they are able nowadays to even generate the model themselves rather than leaving it to signal processing. But then there are two issues. One of them is that there are still underlying domain or modalities in signal processing that may not be observed by the learning system. And the second thing is that when you actually try to apply a learning method, you eventually or inevitably, you need to use method which you use in signal processing. And then, of course, we go back to that uncertainty issue as well. Now, if we have some examples of signal processing and link it to AI, we can go to simple adaptive filtering, which in this adaptive filtering, I'm going to, of course, explain it later. You have a target, and you constantly try to generate an output similar to that target. So what you need to do, you need to build up a model here. And this model receives whatever you have in the input and shape it using some coefficient or some parameter to make that output similar to that DM. And the measure which is going to be used in order to tune this parameter, of course, is a function of that error between the output and your target. So that is adaptive filter. Now you can imagine that the same idea is used, of course, in machine learning and is used in deep learning and neural network systems. Now, another thing which I'm going to talk a little bit more about it this time is so-called cooperative filtering or learning. And I want to say that normally you don't have one observation unattended on its own. Normally you have other measures around itself. So why not? You should be able to use all these measurements around that point. And why not? They should be collaborating together in order to make something happen. Now, and of course, at the end, we come to deep learning. And I talk a lot about this deep learning during my past two talks, even together with colleagues in Porto and in NTU. But I probably refer to that and make a link between what we have in deep learning and, of course, what we develop in the domain of signal processing. Okay, this is what I mentioned about the simple adaptive filter. We highly use it as a signal processing paper, in our theory. So adaptive filters are really another big step in the domain of signal processing and, of course, learning, as you see that. So the idea, of course, is to find a function like J, and this J can be simply a average of the square of error, and that average of square of error can actually be taken differentiation. So you want to minimize this one, then you have to measure that, and this En is this, so make it a square and take a differentiation and use that differentiation actually as the learning factor. So this, so as long as dk and the output, so this is output, as long as the dk and the output are away from each other or different from each other, then that iteration continues. So the less this gets, then the more similar this previous iteration become similar to current iteration, and therefore the system is learned. And at that point is the one that we expect Y to be similar to D. Now, when we come back to adaptive networks, then we are going one step up. So what is happening here? We assume that there are a collection of agents here, that these agents, each one of them is providing a stream of data. So for example, you can consider that you are having EEG recording. And when you do EEG recording, you are actually have each channel as an agent. So each agent is producing a signal. And you can also make different types of link between them. You may go with, for example, different lobes of the brain, or you may go with different the electrodes which are symmetric with respect to each other, or you can go to the whole brain and wire them or rewire them. And if you are, for example, looking at some bacteria, then you can imagine that you have bacteria which are growing, and you should be able to see that if the bacteria is isolated, then of course can be easily attacked by the antibacterial. But when there are few, then they can move around and they can basically follow each other, so make a sort of swarming, and they rebirth and regenerate. So, so we can look at all the components of a system which work together as clever agents. So these agents should interact with each other, and they should be able to exchange or diffuse the information. Okay. Now, of course, the goal is to look at how you can conclude the communication between this agent in order to decide and then later to optimize. So because of that, you can imagine that such a elegant basically method can be used in many, many different areas. Initially, we started on biological modeling and networks. Unfortunately, I don't have that much time to talk about it now, except a couple of slides. But if friends in biotechnology want me to elaborate on that one, maybe later I can elaborate only on application of cooperative networks on these bacteria motility and that sort of type methods. Then, of course, communication system with the sensor communication in rural areas and all these things. Energy and water distribution. Imagine that if all the household can be linked, their meter can be linked together, so they can schedule their appliances, so they don't need really to withdraw a lot of power from the grid on certain time of the day and such like. Housing development, we did actually a project on this one to see how we can get the information from the media, from the internet, in order to decide where we develop the house, the new houses, and where is beneficial to make that houses. And if we make that houses, then what type of houses are more beneficial and more usable and more profitable actually in that area. And then network security is another area. I'm not going to cover any one of them, of course, here, but just tell you what is happening here. Sensor network, smart grid, social network, and also, of course, transportation system on autonomous driving and all these things, and vehicle charging are those important areas. Okay, now, if we have a network like this, then we can imagine that each time we are looking at one agent, and around that agent, sorry, I don't know, there are always problems with these systems. I hope you don't see that bar at the bottom of these slides. On the other side, should see only my slides, hopefully. Okay.
That's what we see. That's what we see. It's very nice.
It's only a slides. Okay.
Yes.
Okay. Thank you. Okay. So if you look at the cooperation here, then if you look at one agent, and we call that agent K, then we can also look at the first order neighbor of this agent and assume that any decision K is making in order to achieve its objective is by collaboration with agents around itself. So there is a neighborhood that we consider around that. So this means that we are going to actually minimize a global function, very similar to the one that we did for adaptive filter, which was a square of error, if you remember, average of a square of error. And then, of course, we need to make it even subject to some constraint. So we can even enforce the constraint into such decision making. Now, if you remember what I had for a simple adaptive filter, I had a W here, another W here, that W was WI, that W was WI minus 1. And then you had this one, which is the gradient of the square of error. Now, we do just a minor change to that in order to make the formulation for adaptive filtering useful for cooperative learning. So what we do basically, we take one of these W, so we change this W to something else, another parameter, And this is the previous W, so it's like the one that we had. And now, each time that we learn in one step, then we combine the information from the neighboring cell, from the neighboring agent. So we basically combine over L. So L can be here, this L, 4, 7, and add them together using some coefficient here. And then when we combine this information together, we plug it into the learning algorithm and go to the next iteration. So that is a whole idea and simple idea of so-called diffusion adaptation on this adaptive network. Now you can imagine that not only you can use this directly, but also many, many problems can be reformulated in this way and can be used. Okay, now the objective of this, of course, in terms of problem statement is that an agent wants to estimate an unknown vector W0, which in this case is phi and psi, from collected measurement, and it has access to scalar measurement dk of I and a m+1 regression vector. So of course, the system model has got m parameters, each one of them, and this m is going to be fixed. And dk, it means the target of the node or agent k. So we have another problem now here. We may have only one objective, but you may have a number of objectives over the network. So imagine you are looking at the brain system, and the brain system is try to assist two physical movement, one hand and one leg at the same time, or one hand and one tongue at the same time, okay? Or even a physical and a behavioral type of activity. So you can imagine that in that case, we have different targets. And if we are going to use this network, we should be able, by learning different groups of agents, we also try to discriminate between the actions of the brain throughout the movement of the leg or foot at the same time, or leg and hand at the same time. So that is what we call it a multitask problem. Now you can imagine that in this case, we only have one objective for K. And in this case, we are going to have each objective for a K which belongs to a particular W, which in this case W is fixed, whereas in this W is for particular group of agents. So you can see the difference between single basically model here and a single task or multitask system. Now, I didn't show you the idea of if you look at I unfortunately I don't have time to show you a video of this Fisher School to see what you are going. Actually, it's probably a good idea to show you that one. Okay, that doesn't matter. Now I try to explain it here. You see, if you look at this very simple video, then you see that there are a group of fish here. And this group of fish, I just run it again for you, they try to reach a target, which is red. So if any one of these small fish here, or prey fish, if you want to call it, is an intelligent agent. And this intelligent agent, it tries to minimize the distance with the target, which is red. And then also they try to keep distance with their alliance, with the neighborhood. So each one is trying to keep distance with his closest neighbors. And then they are attacked by a predator or a shark, for example, and then try to move around each time. If you look at here, and when they move around, they get back together because of that strategy of collaboration. So this is something that you can think that happen in many, many real world systems. Look at, for example, the bacteria. Suppose you have two nutritions here. I'm showing these. Okay, sorry. Suppose you have 2 points of nutritions here, and you have some bacteria which I show it here that there are green and red, and some of them which we supposed to be in the they are dying basically, and the red ones are that they are reproduced, and the green one are the initial bacteria. So now, if these bacteria can get together and understand each other, they can better protect themselves against antibacterial agents. And if they cannot communicate to each other, they may be easily killed by that antibacterial. Look at the next video. This is actually based on that cooperative learning. If you look at the left one, you will see that this antibacterial agent, which we model it by some formulation, is just killing them and come down, and they don't basically move that much around. You know, some of them, they get into the nutrition, but the others, they are not aware that, you know, they cannot communicate with those which are closest to the nutrition. Now, if you look at this one, then you will see that both the bacteria, the initial bacteria, which are the green one, and those that they are regenerated, they immediately communicate to each other, and they get to the nutrition. So just follow that formulation. It tells you really what this one do. And then how they can escape from that bacteria. Now you can imagine that we developed the same scenario for crowd monitoring in COVID time. So you can imagine that if the system can communicate with all the mobiles of the people who are moving or can detect them, they can actually advise them how to run away from something, how to get distance, how to get close to safe area, and all these things that actually we are working on that now, and so on. Now, multitask networking, of course, are the more important. And I told you the objective about multitask networking. So in that multitask, each neighborhood, they have different objectives. Let me just be fast about this. And you can imagine that there are several connected clusters. Now, our assumption is that at the beginning of starting the system, there is no prior clustering information. So that is very important, because this means that based on the action of the agent in that network, you can cluster them. And this is very important. Yeah. So for example, you are in the biotechnology and you are trying to look at, for example, different agents or different materials inside your liquid. And then you put basically a sort of system on that, you know, for this penetration of this material into that. And then you look at the spectrum of that one. You may not need really to wait until the end of this diffusion. You can basically start at the very beginning. And you know, these techniques sometimes takes months for a biotechnologist, you know, to proceed with that. So you may not need to do that. You may iteratively apply this algorithm and look at the behavior of this diffusion from the beginning of this growing or the beginning of this coloring, and then decide up to some extent with what are the clusters, what different materials you might have. So there is no pre-assumption also about the relation between the objectives of different clusters. And so the multitask learning method should use some means of regularization. And that regularization for different, of course, system are different. Now, I don't want to show all these things here. I'll probably just go to the last slide because these are formulations. Sorry, I think, okay, I'll just come to this one and tell you that you have different clusters, and I show each cluster with different set of weights. And I have a regularization, which I already added to our cost function. So this is a regularization system. And if we do regularization, then we need a parameter. And this parameter is the one that it has to be somehow updated and defined as well. There is also a parameter which we call it Lagrangian. And that Lagrangian is the one that basically links in the best way the regularization factor into the original cost function. So now what I did here, I tried to discriminate. I tried to define a cost function in order to discriminate between the clusters. So the same way that we are trying to approach to the center of each cluster, we also make a regularization in order to make the maximum distinction between the clusters. And you see, this is during the performance of the network, not It's not just a steady clustering. And then, of course, there are, again, you are using this cost function, and it changes to iteration estimation of these coefficients of the system. So we do learning, and then we do combination at the bottom. And so the system learns. Now, I was just trying to show you a demo. Unfortunately, it didn't work. But again, we don't have time. Should I go back to the system? So I just show you the overall formulation here, which I combine everything together. So we need to have some sort of adaptation, both on the regularization parameter and also on the combination parameter, and then plug both of them, of course, into the learning system and try to make it work efficiently. I just show you some example. Initially, we did a simulation. So what the simulation, we generated the signal as noise, and we also added noise to that with different variances. So the variance of the signal is more than the variance of the noise. And then we used 3 different clusters with 15 nodes. And then when we run it, let me see whether that link works at all or not, unfortunately. Okay, I try to show you actually how this component moves. So the idea is when you spread the points in the 2-dimensional space, and then you have 3 different objectives, then these points that you spread them around the world, they should go and get to the objective. So if they don't collaborate or the regularization are not okay, you can see it in these 2 cases, in the left bottom and right top. And you see that it doesn't work. If the agents have their own objective and they know already their objective, even without collaboration, they can get to their objective. But now using our collaborating system, we assume that the objects, they are not already clustered. So they are not corresponded to each objective. And then later, the system learns how to get the related points to their objective using this method. But this is very important concept, and there are lots of application for that. And then, of course, we did some assessment, which probably we don't need to discuss about it. We just found out that, you know, with the proposed system, we can get less error. Now, when we come to the context of brain, there is something which we can add to this connectivity. Okay, now assume, okay, something which I didn't talk about it that much. Sorry, I go back. I didn't talk about it, is these coefficients, these A coefficient. So these coefficients are those that we call them combination weights. These combination weights are very difficult to calculate because normally you don't have any idea that what are the extent of collaboration between the nodes. So in the pure mathematics, when they use this, they can just take all the links the same, which is not, of course, correct. Now, when we come to the application to brain, we have a certain problem. We want to know how the nodes in the brain collaborate in order, for example, to move your hand clockwise or counterclockwise. So now, although we have the target, which is hand, and although we have the EEG signal, which are emitted from the brain sources and recorded by the electrodes, but we don't know the extent of collaboration here if we want to apply this cooperative learning for that. Now we have one extra information in the context of brain, and that is connectivity. So we know that for particular action, some parts of the brain are connected and they work in a connected manner. So what we did, we tried to put this together and make this connectivity to link the activity in the brain into your hand movement. So that model is the one we built it up here, based on the combination weights that we can calculate through a connectivity measure together, of course, with running the algorithm, and then make that link possible. Now you can imagine that if you have 2 brains working, one of them is for a healthy brain and the other one can be from a handicapped brain, then you can imagine that this method can tell you how the paralyzed brain, it can follow the healthy brain if they are recorded at the same time. So one can be a target for the other one, or you can generate a target or simulate a target for the one that you're going to monitor, for example, because of a stroke. Now, of course, we did some recording here, and we look at that really, if we just do a clockwise and counterclockwise drawing, how we can classify between these two by looking at this method. So we can actually develop two cooperative filters, and these two cooperative filters are one of them for clockwise, the other one for counterclockwise. And then what we did, we actually managed to do EMG, managed to measure this accelerometer data, and then of course EEG, so we could prove what's happening, so we could verify. So we did a method in connectivity measure. I'm not going to discuss about it. There are many methods, but we use a method called S-transform. And in S-transform, basically, we are using very similar to Fourier transform, but we use a window. And then that window is actually, the variance is like a Gaussian window, but the variance is actually related to the inverse of frequency. So basically, it can, when the frequency increases, it will be narrowed, and when the frequency is lower, it is widened. And it actually works very nice for brain data. Because the events that you have in higher frequency, they are more localized, they are more narrow in frequency. For example, beta rhythm is really narrow compared to, for example, delta rhythm, which is in a wider range, and so on. So it actually works in terms of connectivity very well. And then we measure this connectivity actually using these parameters. And then we measure this X, we multiply them together, so cross-correlate them together in the time frequency domain. And out of these, we measure these measures of correlation. And this correlation measure is later used in the connectivity measure. I'll come back to that, of course. And then you will see, for example, for simulation, if you have connection between electrode 1 and 2, you can see that these two electrodes in 20 Hertz, they show that red in this connectivity domain. Or if 5 and 4 and 3 are connected, then you can see that from 4 to 3, which is this point, actually this window, you can see it is highlighted. So you can see very nicely the connectivity values in certain range of frequencies and around certain time. You can measure from this. And then you plug this one into your algorithm. So now you take that, you measure from those CKL that I told you before, imaginary part of those values, which are their complex. And then you normalize it. So this is just normalization. And then you get this value. Now these values are counted as your combination weights. And then it can combine the electrode information or the weights you generated already and plug it into that iterative adaptation or learning system. So with that one, and the interesting thing is that the connectivity measures are reasonably consistent. You see, over time, you can see that some connectivities, I show it, for example, between which electrode and which electrode, they are not really that much mixed together, although some of them are mixed together, but doesn't matter, we can ignore them. But some of them are pretty distinct, and they remain the same during prolongation of the hand movement. That is very interesting. And then when you classify that, you can classify up to about 70–80% between two classes of subject 1 and subject 2. This is very important again, because now it tells you, for example, that around which combination of, for example, if for example, if you divide in different frequency bands, or you divide it between different time space or whatever, then it tells you exactly around which areas you have the maximum discrimination between the two, and you have the best classification rate as well. So you see, actually we used a purely signal processing concept in having a classification for a prolongation of the movement. Now, this is still a single task problem, yeah, because we only did a movement, only one hand. Now, we can do the same thing for Parkinson. And for Parkinson, we can go to multitask, which one of them is actual movement, and the other one is the related tremor. Of course, looking at the tremor of the hand from the brain is, again, another challenging. So I forget about all this theory, and I just show you that you can see here that if you forget about the beginning of this trial, because it's to do with learning. Sorry, how much time I have?
More 5 minutes, I would say.
Okay, thanks.
Okay.
Okay, so you can see that really that when the hand is on rest, and then when it is on rest, actually the movement, the tremor starts. When try to catch, the tremor stops. And then you can see, even without any classification, without anything, and looking at what we have out of the sensor hand, you can see this rest time is pretty correlating with the time that the hand is rest, and you can see it with the motion sense. And you can detect it from the EEG, whether the hand is on the tremor and in terms of movement is on rest or not, which is, of course, not perhaps very accurate, but very important. Now, another thing that we did, we look at also the cooperative ERP tracking. I just show you. You know that for the ERPs, if you have a target, which is the blue one, you can easily, very nicely see P300, P3A, and P3B. When it is regular target, you may see that the P3B is going to collapse, reduced in terms of size. And when you have a standard stimuli, hardly you can see even the component of P3A. And of course, how you can benefit from this fact is that normally in terms of ERPs, they are bilateral. So it means they are symmetric in terms of both sides of the brain. So why not you use this symmetricity? Now, when we try to combine this electrode together and use this symmetricity and try to do a tracking. So tracking means there are some parameters. We combine them together and see how they change. What are these parameters? The parameters are a number of parameters for P3A, a number of parameters for P3B. The parameters include amplitude, latency, and width of each one. And then we do tracking. And we do over single trial. We don't do any averaging, okay? So when we combine together, you know already, because we used a schizophrenic patient and healthy subject, you know that we use different methods, and it is very nicely can be measured that for a schizophrenic patient on the top, you can see the P3B is highly reduced. There is a bigger latency, lower amplitude. And when it is healthy, you have bigger P3B for the target. And then you have lower latency and higher amplitude. So these are the things which are well established. And we can use different methods in order to clearly measure this one. But now look at here. For a healthy subject, you have measure over F3 and over P3, if you look at, and I'm looking at P3 and P3B. So if we look at the healthy subject, and you can see the position of green and red, of course, changes over F3, which is frontal, and P3, which is posterior. And this is peak amplitude, this is peak amplitude, this is over F4, this is over F3. So you can see they are pretty similar, actually. If you look at both of these guys, they are very similar. These two are also very similar. Now, when you come to a schizophrenic, you can see that the amplitude is reduced highly. That's based on the measurement. Now, look at the latency of the healthy one. So these are the latency again, and these are the latency. And when you go to a schizophrenic, then you see that the latency highly increased. You see, this is obviously a schizophrenic latency and such like. Okay. Anyway, I'm almost there. So there are well, this cooperation can work in a lot of very, very delicate type of data. You know, you might have different types of data which are completely different with different origin, like this one. You know, you have central beta activity. It can come up like this. And of course, you can localize this within this system. Now, if you go to this one, you may have something similar, narrower in terms of length, but this is actually a seizure, proximal fast activity, yeah? And you may have even sleep spindles, which they may be short or longer in duration, but around a certain frequency. Now, what makes these things different from each other is that makes similar, they are periodic. What makes them different is the location. So now we can actually look at this collaboration using something which we call it cooperative adaptive line enhancer. And then we can discriminate between them. So basically, again, we do measurement of this activity, we plug it into the system, and then we do this adaptation. And then you can see really that the discrimination is pretty accurate. You know, when you do collaboration with this method and you use just something like SVM in doing this between the two, then you see how the accuracy is increased. Okay, and I think I mentioned before about IEDs. I go to last 3 slides that I wanted to emphasize on that one. Forget about this thing that I talked about it before. Something is important. When we label the data, we involve uncertainty. So in the context of seizure, we ask the physician to actually tell us with what certainty level they label the data. And this is what they have. So 10 means 100% sure that these spikes are IEDs. They are intracranial, as interictal epileptiform discharges. And the lower is low. Now, we tried in our last attempt to incorporate this uncertainty into the system. So forget about this one, and I go to the last bit, which I use tensors. And these tensors are multidimensional systems that the concept is borrowed from linear algebra. And then it allows you to incorporate various diversity in time, frequency, space, subjects, trial, shape, everything in one multidimensional entity, and then try to analyze that. So now what we did, of course, we did a lot, this tensor. We nicely removed artifact, for example. We nicely detected readiness potential for those people who want to know about this. We have lots of papers and software ready. And then when we come to this last bit, is the one that we try to find some components in a matrix form that can be by decomposition of a tensor of multidimensional, that when we know this component, one is referred to the spatial domain, one referred to frequency, one, for example, to time, one to segments, or one to trial, the other one to subject, we have uncertainty. Now, we added another tensor here, which in that tensor that we find it through this unified algorithm, we incorporated the uncertainty. And this is the way we incorporate. So we said, for example, if the score is highest, we have the component of this W equal to 1. If it is 1 with lowest uncertainty, we put a small value of 2. But we know that uncertainty is a cause here. So we don't attempt to change anything. We just multiply this by the whole system, and still we try to find these components. And now when we do that, of course, through some method, we just published this one, then we see that, for example, a spike can be nicely detected, for example, when it is completely localized around a lateral system, temporal lateral system. And this decomposition allows us to say in which domain the classification performs best, either in time, frequency, space, subject, trial, or the morphology of the filter. So that gives us a more universal or more unified way of finding the domain which the best classification can happen. And I think that's all I did. Thank you very much. And sorry if I took a lot of time.
Thank you. Okay, right now we have time for 2 or 3 questions. I guess we already have some questions on our chat.
Let me go to. Okay,
I think
it's
you
fine.
have assessed
Unshare
it.
the screen. Okay, I think it's unshared already. Yeah.
Yeah. No, you still with your screen share with us.
It is interesting. It shows that. Okay.
Okay, but it's okay.
It looks that it is from your side, I guess. Can you see whether you can unshare it?
Maybe Dr. Maria can.
Yes, I'm trying to.
Okay, I just do share again and unshare. And
no, it's just stop sharing, Professor.
Okay.
Okay, but
okay, it shows me that I can share, but what I can do actually, I can just now
I did it.
okay.
I managed.
Did it actually.
Okay.
We have some questions on our chat. Gisela Espaiva, tell us when you speak about cooperative networks in biology modeling, can it be used for something like remote diagnosis?
When we talk about biological modeling, we can have different types of measure actually. If you are measuring locally, for example, if you are just looking at one pattern of bacteria, then in that case everything is very local. But when we are taking a measure from a wide area sensor network, for example, in a rural area, in a jungle or something like that, then obviously we attempt to use this and as both learning and decision-making system and try to look at where there is any anomaly or abnormality in the system. Yes, of course, that is one of the objectives. So of course, we can do remote diagnosis. Every sensor can be equipped, of course, with remote system, with wireless system. And there are many other things we have done. If you look at the papers that we did, we look at what happens if even one of the sensor fails or dies. We did if what happens if one of the sensors sends even wrong information, how the rest of the system can recover. So there are many things actually in this one. So if you mean that this biological modeling is across a big area, then as long as the sensors are there and can communicate wirely or wirelessly, then yes, it should be able to do that. Yeah.
Okay, let's move on to the questions of Gabriel Silva. What you advise? He needs your advice.
Well, this is very wide. This is very wide, but you can look at more, of course, what is the top area. I mean, to me, nowadays they are referring to personalized health, of course. And personalized health is the one which try to have a local link first, and then a global link. And local link means obviously body sensor networking, which you need to have a good collection of measures from over the body. The second stage is how these can do onboard processing, so they can have decision locally, and then they transmit their decision globally. So I think this is very elegant area for those people who like to do technology and measure. But you can use this method even if you are going to do, for example, on the IoT. IoT nowadays is very
yeah, and one
but this is digital.
challenge.
No, digital health can be incorporated within, of course, IoT, but this is not personal health. This is more global. I think personal health now is very important.
And one of the biggest challenges is to get data. Sometimes I don't know in UK, but in Portugal we have a lot of procedures and bureaucracy to get a lot of data in the medical area.
That's sure. The reason I mentioned about personal medicine is because you don't need to broadcast the data. You just need to broadcast the decision.
Okay.
So the good thing about personal medicine is that you basically collaborate and use the data locally So that is the most important advantage of that, I think.
Okay, let's move to
now. Data plays
question.
a key role in signal processing, and its large-scale acquisition for method validation is sometimes difficult. Well, of course, data plays a big role, but it plays a big role in machine learning nowadays because of the rise of generative models. Generative models are becoming very, very useful in the system because data is available and the system try to make sense of the data. So that is the important thing. Now, in terms of validation, we have different methods in learning system. In learning system, we have batch learning, we have global learning, we have batch learning, and then we have mini batch learning, and we have sample learning. So now, if you want to know what I mean that exactly, is that not necessarily every information is to be tested. Sometimes you receive an information that this information is already known what it is. You should be able to plug it into your training system very easily. This is the objective of so-called mini batch learning system. They use it nowadays in deep learning. Now that is important because as long as you have some validated data with the specific target, you can not only use it for testing, but also you can use it to boost your training. So this is the nice thing that you can do generally. But in terms of validation of the data, of course, it's not something that you can easily say, especially with involvement of uncertainty. You're right. I think it is difficult to say that you can do all validation. There are always level of uncertainty there.
Okay, let's move on. Gabriel Silva again.
It would be possible to use this method in terms of connectivity in them. Of course. But the thing is that in now dementia, if you really have access to dementia data, then you can certainly, we already proved actually that connectivity is the best measurement for diagnosis of dementia. Not only us, but also our friend in Riken, Japan, and in Nanyang, Singapore, all of them, they have publication that connectivity is very important. But now we can do one step up. So we can have one dementia person to do particular movement. And that particular movement can be a target. So you can also not only do the connectivity, but you can use the connectivity in order to measure the combination weight for your adaptive learning or cooperative learning. So you can make it now one step up. Connectivity is already proved, but you can make it even better by giving some physical task to the dementia person. So that is the beauty of cooperative learning for them. Okay. One of the areas that I can read that from Pedro. One of the areas that has been becoming more and more deeply interconnected to AI and by extension signal processing is big data, which the rise of biomedical big data, how will the technique of it? First of all, big data is a name which still is a bit ambitious. You see, initially, when the name of big data came, it didn't necessarily refer to the size of the data. It also referred to how the data is distributed. Okay, so if you have, for example, huge data, but each part of, if all the data can be accommodated in one core, in one computer, I may be very reluctant to call it big data. But if the data is distributed over different cores that you cannot process it in one core, then that is a good place to call it big data. So you can imagine now that a distributed system is a solution. Because at this, I can show you even one nice demo on this one by using tensors, that's how we can solve this big data problem. So deep learning and tensors in parallel, when they work over multiple cores, they can solve completely this big data problem. Well, I cannot never say anything so confidently. I cannot say completely, because we have one other area in that. And the other area is multimodality of the data, because not all the data are in the same modality. So now you can imagine when we have big data, it means we have huge data which is located over multiple cores. And over different core, you need to be able to process it up to some extent and then deliver a low-graded or lower dimensionality data across the cores in order to be processed. So that is a subject that a friend of us, of course, in United States, also Calhoun, gave a nice presentation on that one. I think it was 2016, and then developed a bit more on tensors. Tensors are good actually in dealing with big data. And deep learning, of course, if you can make it multi-core. And now Alicia in my group actually is doing these adversarial generative networks in order to build up a cooperative networking using generative adversarial network in order to solve this problem. Hopefully, if we can get some idea of or we get to somewhere, then we come back to you. Okay, now we have
2 questions.
Robot. First, thank you. Okay, thank you very much. Would like to know a little bit more about which are the techniques software used to remove the artifact and try to well, which artifacts you're talking about? If it is on EEG analysis, oh, we have plenty. We have at least 4 or 5 different ways of removing the artifact. But again, to be honest, the best one was Tensor one. For removing artifact. But in 2005, we published a paper using simply blind source separation plus support vector machine, and still it's being cited. And it was very effective. But then later, I can send you, if you send me an email, I can send you a number of papers, different methods that exactly tell you how to do that. Okay, I can send you this one. Just send me email, please. Okay, Patricia, thank you, Patricia, to you, actually. Interested in quantifying the inherent coordination between interacting individual, and I'm talking about EEG signal. Okay, hyperscanning, preferred measure, or even body movement. Do you mind elaborating a bit about what is the more reliable approach, the moment to quantify physiological linkage or synchrony within that space?
Before you ask Patricia, she is with us. Patricia, if you turn your microphone on, you can talk a little bit with Professor Saeid.
Yeah, Patricia, you want to? Yeah. Okay. Sorry, let me see.
Patricia, you are now available. Yeah.
Oh, okay. Thank you, Maria. Hello, Saeid.
Hello, Patricia. Yeah, please. Maybe there are too many questions there, so.
Yes, I know. I'm so sorry. So
that's all right. So, what is really the target question here?
Yes, maybe the first, the more important one is related with the more reliable way to treat the synchrony within data. So that's very challenging because we have here many decisions, such as with lag, without lag, what type of approach, what type of specific metrics we will look for within each data sign, because we have 2 different sources of data, right? 2 persons interacting in real-time life. So this is a messy in the literature because we do not know how to analyze synchrony within a dyad. And I was just thinking that maybe I was trying to use some of your approach, trying to think, okay, maybe this is useful to do this. Especially we have many peripheral measures. As I told you in the past, we have ECG, EDA, we have respiratory frequency that we collected when a couple, for instance, a romantic couple was talking about positive and negative aspects of their relationships. And what we want to know now is that if we have a lead For instance, if one of them is influencing more significantly the way the other is reacting, or if we have a pattern that one is a mirror of the other. So there is many different approaches here, but I was just trying to ask you if you can recommend any specific approach for synchrony or coordination. I don't know, we can call for different names, right?
Yeah. Well, it's very good question. And of course we have been after such a thing, but please think about two issues here. One of them is the word synchrony, because if you key in synchrony in the context of brain, it probably doesn't lead you directly to the connection between two brains, for example. Or it doesn't necessarily lead you to the similar or conflictive actions that the two persons, when they interact to each other, they may have. So you may need really to try connectivity rather than synchrony. Synchrony is used basically in the context of seizure or similar type of problems, because only in the case of a generalized seizure, then you can see that different lobes of the brain are synchronized and generate a particular frequency range signals. And when you also refer to synchrony, the people try to discriminate it with chaos in the context of brain, whether the brain is more chaotic or whether the brain is more synchronized. So I prefer scientifically to go to connectivity action. Now, a number of people in Italy, they are all friends, of course, Fabio and all people, they try to find a sort of, by simple classification and connectivity measure, they try to find out when the people do a sort of similar type activity, like, you know, liking each other or like to do the same thing or try to respond to each other positively. Try to make not only a measure of connectivity in each brain separately, but also try to find a link between the two brains and compare it with when they do a competitive game. So the only thing they managed eventually to do was to discriminate between a collaborative and a competitive action. That's all they tried to do. Okay. Now you're looking at emotions. Emotions are very, very nice in terms of context that have to be looked at, but they may not necessarily have the same response as collaborative or discriminative action, because in those actions, the brain activity is linked to the physical activity, whereas in your case, you are looking at the mental activity. Yes. So I believe that it would be wonderful if you really just make this connectivity measure within and between the brains, and then think about how you can process or classify it.
Do you think we can call connectivity even if we are talking about peripheral measures or behavioral data? That's the right word as well. Yes. Because connectivity, yes, I mean, seems very connected to brain, right? Maybe because this is the type of data signal that we use more the term connectivity.
Mm. Well, you see, your peripheral data is not something just that you measure. There are other types of peripheral that you are not aware of that. For example, you don't know whether the brain is in the relaxed position or not. Okay. So that relaxing brain can be measured, of course. Or when the brain is agitated, for example, because of the conflicting or competitive action, then it can be measured. So these are other peripheral data that you can directly measure from the data rather than doing other equipment to measure that one. I guess yes, it is possible. It is possible, yes. I think probably a combination of tensors and connectivity can work together very nicely, yes.
Fantastic. Thank you so much, Saeid. And yeah. I'm sorry.
I think about it more and then come back to you, because we have thoughts about these things, yeah.
Yes, thank you so much. And please, Pedro, I'm so sorry. Please give me just 15 seconds and let me join you in a comment, in a specific comment. Your work is fantastic in itself, no doubt, Saeid, but there is something else I sincerely appreciate on you, because being a senior researcher, super busy, involved in an astonishing number of networks, you always have your door open for new researchers like Pedro and me, who love to share with you crazy ideas. Maybe we have shared more delusions than ideas about very ambitious project we want to initiate, and you are always available to discuss with us. Thank you so much. I really appreciate that.
I'm really proud of that, and I hope that we can find many grounds to collaborate. Although I'm getting old actually, but still I have a lot of people around the world that they like to work with me. So they're always waiting for some problems to solve and all this. And I think that always the good research is the one that it has a certain level of risk in that. And there are ambiguities in that. And a huge level of uncertainty. So that makes me more excited, and I like to follow that. Yeah. Thank you. Thank you very much for inviting.
Thank you very much. To finalize this keynote, I have just one question, and in your point of view, how far we are from a machine decision-making ability without being training really for it?
I think with the new, these generative models, we have a big advantage, of course, in moving to learning everything. So, you know, if you look at some other things which probably you haven't heard about, this they call it class. I just forgot it. Sorry. There are new methods actually that they try to put the data and the methods and the coefficients of the method and everything, and try to learn all in one shot. So something like broad learning. If you key in broad learning, they are using that one. So the generative models are very, very useful. And I think we are, except one problem that I'm going to mention about it, we are probably moving into using generative model to do all this processing for us. And the only problem that we have this generative model is that at the moment, as I see this generative model, they don't look at the diversity. So diversity is important. You know, in 5G systems, communication system, the reason 5G is better than 4G is because they are using a spatial diversity. So basically, they can target to 10 mobiles on your table, 10 movies, which they are broadcasting in the same time around the same frequency, just because they are different in a space. Now, diversity is something which still is not fully exploited by generative model and deep learning. And this diversity can be a combination of everything together: time, space, frequency, subjects, trials, everything. So a system should realize this, you know, all this, and link it together. We have one paper that we try to use 2 LSTM together, one in time and one in frequency, and link them together. But we didn't find any way to have one LSTM to do both of them at the same time. And our measurement was actually to find out whether a cow is lame or not lame. So you can imagine.
Yeah.
Now, if we could use something like LSTM that could use both time and frequency at the same time, then that would be very nice.
Yeah, it was still far away. It's still a big challenge for everyone in this area. Okay, thank you so much once again. And okay, we finished this keynote right now. Thank you.
Thank you very much. Thank you. Have a nice day, and also have a nice weekend, as tomorrow is going to start.
Nice weekend for you also. Thank you.
Thank you so much. Now, thank you so much, Professor. And now we are moving on for the closing session of our students' biotechnology event.
Okay, thank
We
you.
are pleased if you want to stay or... Ok. Agora em português, o professor Saeid já saiu depois de uma conferência que foi muito participada, muito boa. E agora passo ao Eduardo Apolinário, membro da Comissão das Jornadas de Biotecnologia, que sei que foram um sucesso. Muitos parabéns aos nossos estudantes e passo-lhe a palavra, Eduardo.
Muito obrigado. Eu queria, infelizmente queria agradecer ao professor Saeid, mas já foi embora. Também agradeço ao professor Pedro Rodrigues, mas agora infelizmente estamos a chegar ao fim, portanto vou dar o início ao fim das Jornadas de Biotecnologia 2021 e para tal nós temos a nossa sessão de encerramento. Para começar, eu passo a palavra à Presidente do Centro Regional do Porto, da Universidade Católica Portuguesa, a professora Isabel Braga de Cruz.
Muito obrigada, Apolinário, por estas palavras. Eu gostaria de agradecer a presença de todos. Bem, enfim, primeiro cumprimentar a professora Paula Teixeira, que eu penso que também se junta a esta sessão de encerramento, o Francisco Silva, na qualidade de presidente da Associação de Estudantes da Escola de Biotecnologia, a Maria de Mel, e na Maria eu, enfim, cumprimento todos este staff e esta equipa fantástica que conseguiu tornar este sonho realidade, e só tenho provas disso. Aliás, os ecos que eu fui ouvindo da estação foram muitíssimo bons, muitíssimo participada, como nunca. Realmente o online traz esta grande vantagem de conseguir ir buscar pessoas de outras geografias que se calhar numa situação normal não teria sido possível reunir este número de presentes. Obviamente cumprimentar todos os presentes e durante 2 dias de uma forma tão intensa, até este momento, enfim, de uma sessão de encerramento já em cima da hora do almoço, os oradores, os professores, os alunos, até os alumni, enfim, toda a capacidade mobilizadora que eu acho que é muito invejável e que hoje aqui estamos para felicitar. O tema foi absolutamente bem escolhido, não podia ser mais pertinente, o tema que foi presente sempre ao longo de todas estas sessões, de alguma forma mais ou menos indiretamente, portanto, basicamente o tema da saúde mental. E aqui uma nota especial também para esta responsabilidade social que acabaram por conseguir suportar de uma forma indireta com esta iniciativa uma associação que acaba por ser uma iniciativa muito bonita e que também se liga aqui à missão da Católica. Eu só tenho a agradecer, não é para me ouvirem que aqui estão, acho que é um gosto muito grande para o Centro Regional do Porto e aqui onde a biotecnologia obviamente está incluída, poderam acolher um evento como este, e tenho a certeza que a fasquia está muito alta e para o ano vai ser superada, claro, e vamos ainda conseguir tornar, ou pelo menos manter esta dinâmica que é muito meritória e que todos gostamos muito. Portanto, passem bem, estejam todos de saúde também. Aproveito para desejar também uma boa Páscoa e passava a palavra ao orador seguinte. Muito obrigada.
Muito obrigado, professor. Passo então a palavra à diretora adjunta da Escola Superior de Biotecnologia, professora Paula Teixeira.
Boa tarde a todos. Eu também começo por cumprimentar os colegas deste painel de encerramento, a professora Isabel Braga da Cruz, portanto, presidente do Centro Regional de Porto, o Francisco Silva, que ainda não vi, mas penso que está aqui também, presidente da Associação de Estudantes, a presidente destas jornadas, a Maria de Melo, e, obviamente, todos os restantes membros da comissão organizadora destas jornadas e todos os que, de alguma forma, contribuíram para o que foi a excelência do evento. Portanto, eu vou repetir um bocadinho aquilo que foram as palavras da professora Isabel Braga da Cruz, portanto, não há como fugir. Portanto, estas jornadas foram mais um exemplo de que as crises podem gerar oportunidades e, portanto, no momento em que estamos a vivenciar, esperemos a passar uma crise, a Covid, portanto, seria muito mais fácil adiar as jornadas para um momento em quando fosse possível termos o evento presencialmente. mas tivemos um conjunto de estudantes que de facto se mobilizou de forma extraordinária e trouxe a estas jornadas um conjunto de temas de grande relevância e atualidade e apresentado por investigadores e outros profissionais também da excelência e que provavelmente alguns teriam tido dificuldade em participar se o evento tivesse sido presencial. Para terminar, e também não posso deixar de referir que, ou seja, a forma como terminamos também foi uma forma de excelência, porque juntamos aqui a estas jornadas de biotecnologia uma conferência no âmbito das comemorações dos 30 anos do nosso centro de investigação, portanto, o CBQF. Portanto, muitos parabéns, muito obrigada à Comissão da organização destas jornadas, portanto, uma excelente oportunidade de aprendizagem e de partilha, e que acho que ficou bem patente a relevância das colaborações multidisciplinares. E também não posso deixar de vos felicitar pela iniciativa de promover, ao apresentar, e de também contribuir materialmente para a associação encontrar-se. O Francisco Silva ontem criou-nos aqui na sessão de abertura grandes expectativas, quando referiu que estas iriam ser as melhores jornadas. É assim, eu tenho assistido a várias jornadas e, portanto, não vou dizer que estas foram as melhores ou não foram as melhores, até porque já não me recordo de muitas das jornadas passadas. Agora, é assim, se foram as melhores, portanto, não sei. Aquilo que sei é que foi um evento de elevado nível, de que a ESB muito se orgulha, portanto, organizado pelos nossos alunos, e que eu acho que colocou a fasquia para quem vai organizar as próximas jornadas num nível muito elevado. Mas, portanto, os alunos da ESB têm sempre uma capacidade de nos surpreenderem, portanto, eu acho que isto que não será um problema, de qualquer forma é um grande desafio. Portanto, mais uma vez, muito obrigada, muitos parabéns e obviamente contem com a direção da ESB para colaborar nestas vossas organizações. Obrigada e passo então a palavra, penso que ao Eduardo.
Muito obrigado, professora, pelas suas palavras. E agora passo a palavra ao Presidente da Associação de Estudantes da Escola Superior de Biotecnologia, Francisco Silva.
Obrigado, Eduardo, e bom dia a todos. Cumprimento mais uma vez a professora doutora Isabel Braga da Cruz, Presidente do Centro Regional do Porto da Universidade Católica Portuguesa, a professora Paula Teixeira, diretora da Junta da ESB, e também cumprimento a Maria. Bem, como se costuma dizer, o que é um acaba depressa, não é? E chegou ao fim mais uma edição das jornadas. Como já disse, dou os meus parabéns a toda a comissão organizadora pelo evento que fizeram. Eu penso que todos, ou quase todos, concordam que foi uma das melhores edições, pelo menos, agora a responder ao que a professora Paula Teixeira disse, pelo menos nos meus 4 anos de jornadas. E as palestras, lá está, foram interessantíssimas. Eu, infelizmente, não fui capaz de estar em todas, mas pelo menos as que ouvi foram muito interessantes. Dou também os parabéns pelo número recorde. Eu vi quase sempre o número de participantes acima dos 100, ali em baixo, salvo eu, o que é ótimo. Por isso lá está, o online também traz as suas vantagens, o que é ótimo, e por isso os meus sinceros parabéns pelo trabalho. E agora, para não me alongar muito, resta-me também dizer que foi um prazer estar na sessão de abertura e agora na sessão de encerramento. Para o ano, muito provavelmente já não vou ser eu neste lugar. Mas pronto, em nome da Associação de Estudantes, foi um gosto contribuir, nem que seja um bocadinho, para a realização das jornadas. Despeço-me de toda a gente. À Comissão Organizadora, mais uma vez, um excelente trabalho a todos. e obrigado. Passo a palavra ao Eduardo.
Muito obrigado, nosso presidente da nossa Associação de Estudantes. E, por fim, passo a palavra à pessoa que muito fez por este evento, um pilar da comissão organizadora, a nossa presidente das Jornadas de Biotecnologia, Maria de Melo Rodrigues.
Obrigada. Queria começar então por cumprimentar a professora doutora Isabel Braga da Cruz, a professora Paula Teixeira e o meu colega Francisco, da Associação de Estudantes. Bem, mais uma edição que passou e eu acho que correu tudo muito bem. Espero que todos tenham gostado assim como eu gostei. Estou aqui a agradecer mais uma vez a presença de todos vocês. Queria dar também um agradecimento muito especial à Católica pelo apoio aqui no Zoom, nomeadamente à Patrícia Fontes e à Maria Lopes Cardoso. Também um grande agradecimento à direção da ESB e a todos os professores da Comissão Científica por todas as palavras de carinho e por todo o apoio que tiveram connosco. Neste momento, devia estar a entregar certificados aos meus colegas da organização, que tanto merecem porque o trabalho que nós fizemos foi imenso. Infelizmente não é possível, tenho que ir virtualmente, mas quero que saibam que agradeço de fundo de coração este acompanhamento ao longo da organização deste ano e que tenho muito orgulho na equipa que liderei este ano. Pronto, agora para ser mais pessoal, queria agradecer à Ana, à Eduarda e à Maria Martinho por me acompanharem na presidência. Às restantes, André, Daniela, Eduardo, João, Maria Ana, Mafalda Lamas, Mafalda Oliveira, Miguela, Rita, Simone e Teresa, um obrigada muito especial a alguns de vocês por continuarem desde o ano passado e nunca desistirem, e a outros por se terem juntado este ano e por todo o trabalho que têm desenvolvido. É de salientar que nesta edição tivemos alguns contratempos que não estávamos à espera, mas conseguimos ultrapassá-los, e aqui é muito visível a nossa capacidade de trabalho em equipa e resolução de problemas, que são duas das muitas valências que as jornadas nos trazem. Estou muito orgulhosa por ter sido presidente este ano, mesmo que tenha sido online, pois trouxe-me novas experiências que tenho a certeza que nunca esquecerei, e os meus colegas também não. Aos participantes, por fim, espero que tenham tirado proveito deste belo leque de oradores, e fica aqui o meu apelo para voltarem para o ano, porque as jornadas não ficam por aqui. Um bem-aja a todos e até para o ano.
E com essas palavras dou como terminada as Jornadas de Biotecnologia 2021. Muito obrigado a todos que estão aqui e aos que estiveram aqui. Espero que tenham desfrutado tanto como nós e espero voltar-vos a ver daqui a um ano, desta vez cara a cara. Antes de toda a gente ir embora, eu vou colocar um link no chat, que eu peço que toda a gente responda, por favor. E outra vez, muito obrigado e até à próxima.
Ok, Eduardo, precisa de ajuda?
Não, estava aqui a procurar do link só. Okay.
Ok, enquanto a malta não sai.
Aqui. Obrigado.
Ok. Muito obrigada, um bom fim de semana para cada um.
Um bom fim de semana para si também. Muito obrigado.
Obrigada.
Obrigado.
Obrigada.